Yeah, welcome student. Welcome to today's class. So let me start. So this is MA415 Algebra. Okay, and this is lecture number I think 24. Okay. So today we will learn two very special type of ideals. Okay. So. Let me start with the first one. So it's called prime ideals. Okay. Yeah. Throughout this today's lecture, I will assume that R be a commutative ring. Okay, this is my assumption. Commutative ring. Okay, so if it is not commutative ring, then also you can define this prime ideal, but in little bit different way. But let us just assume this thing. Okay, definition. So a proper ideal P proper means is cannot be full ideal, full ring. Okay, P is said to be a prime ideal of R if for any two elements say x comma y belongs to R. Okay, so maybe this is okay. If x into y belongs to P for any xy belongs to R, either x belongs to P or y belongs to P. Okay, so yeah, so this is the definition of prime ideal. So prime ideals are cannot be the full ring, and whenever some product of two elements belongs to this, that implies um, mm, either x belongs to P or y belongs to P. Okay, so this is the mathematical definition of a prime ideal. Okay, now let me give some example and let me see you how this is actually generation of notion of primes in rational numbers. Okay, or integers, whatever, rational primes. So examples. So you see inside the ring of integer z, so if you have this r equal to z plus dot. Okay, so you see that for example you take that ideal generator 5. So what is this? This is 5z. This is all the integers of the form 5 into n belongs to z. Okay, it's called 5z. So you see that this ideal is actually a principal ideal generated by a single element. So that's why I'm writing by this. So this is actually prime ideal. For example, if you choose some element, say let say x and y belongs to z such that x time y belongs to 5z, suppose. So what does that mean? That means the product is a multiple of 5, right? So that means that implies xy equal to some 5 into k, right? For some k belongs to integer, right? But then division algorithm, you just use that 5 divides these both sides. So this implies 5 divides x into y. Okay, now 5 is a prime number, right? If a prime number divides something, then it has to divide one of these things. So this implies either 5 divides x or 5 divides y. It can divide both also, doesn't matter. Okay, it can divide both also. So this is not like exclusive or the inclusive or. Okay, either this or both. Okay, so what does that mean? So if x divides 5, so what does that mean? That means x belongs to that 5z, right? Multiple of 5. Or y belongs to, in this case, y belongs to 5z, right? So what does that mean? That means if the product belongs to that in the ideal, then at least one of them belongs to this, right? So that means that this ideal generated by 5 or whatever I wrote by this is a prime ideal, right? Prime ideal in Z, right? Right. Now you see that 5 is not a special element. It is true for any prime number, right? So if you choose any prime number p, then this is p times z. Okay, is equal to is a prime ideal in Z. I just only use that the property of primes, right? So exactly this is the generalization of prime numbers, what you learn in schools, and it's called a prime ideal. Clear? So now maybe you can have many more examples. For example, the zero ideal inside Z. Okay, you see this is a prime ideal. Right? What does that mean? That means if the product equal to 0, product of two elements is 0, then at least one has to be 0, right? So this is prime ideal. So this is an example. Maybe you can choose many more examples. So maybe you start with say so zx we have already discussed, right? Zx, that polynomial ring over integers. Inside that you have a ideal say generated by x. So this is an ideal, right? Now you see that this is a prime ideal. How to prove this? Okay, so simple. Again, you need to use a division algorithm. Okay, so if you choose two elements product inside this, so let fx and gx belong to zx such that fx into gx, the product, is inside this ideal generator x. So what does that mean? That means it is of the form, this belongs to this. So that means what? That means this fx and gx will be of the form x times some hx, right? For some hx belongs to zx, some another polynomial. So now x is independent, right? So x divides this product. So what does that mean? So that means x is sitting inside either this fx or gx. So this implies x divides fx gx, right? And so there cannot be so the product cannot have a constant term. Constant term has to be 0, right? Because here the constant term is 0. And so that implies that either x divides fx, that constant term of fx is 0, or x divides gx. Okay, so either fx belongs to this ideal, or Gx belongs to this idea, right? So this is ideal generated by this into X is a prime ideal, right? Clear? So this is the definition of prime ideal, and this is, you can easily find out that you can check what is a prime ideal or not. Yeah. And now there is one more way to find out something is a prime ideal or not, and that is a very important theorem. And we will check something is prime ideal or not using the quotient ring. Okay. So so let me write down the theorem. So this is the assumption that let R be a commutative ring, okay, and then an ideal P is a prime ideal of R if and only if and only what happens if and only if the quotient ring R mod P is an integral domain. Okay, this is if and only condition. So what does that mean? That means if you want to check something is a prime ideal or not, you take the quotient ring, and if the quotient ring is integral domain, then you are done. It's prime ideal. And conversely, if the quotient if a prime ideal, if start with prime ideal, then quotient ring will be always integral domain, right? Now before going to the proof, so let us check that in the previous examples what I was discussing here. In this example, see. Now, in this example, this is I use the other definition, but you can use what I just discussed here. That also you can use it. You see that ZX mod this is what this is. We used it last class that this is isomorphic to Z, right? In first isomorphism theorem of rings, and this is you see that this is a integral domain. This Z is an integral domain, right? Integral domain. So what does that mean? That means this is a prime ideal. This is you can easily also you can check prime ideal. Okay, so this is another way of checking this. Okay, so now we will give a proof of this statement. This is a very important statement, and this idea is going to use many times. So proof. So that this is there is a if and only condition means what? That means you need to prove both sides. So you first assume that one thing is true and then prove another thing is true, right? So which one you want to prove true? So let me assume that. So let um, P be a prime ideal in R. Okay. Let us assume that P be a prime ideal in R, and then what you can say? Then you can say that okay. So what I need to find? We need to prove that R mod P is an integral domain. Okay. Now consider. So consider. So let me write down this is P bar is R mod P. Okay. So to show something is integral domain, what I need to show? I need to show that there is no zero divisor, right? So there is no zero divisor means if you take two elements whose product is 0, then at least one has to be non-zero, right? Both cannot be non-zero. Okay, now let I choose two elements, say x bar and y bar belongs to p bar. So what does that mean? That means c x bar equal to something, say x plus p. This is question ring, right? Similarly, y bar equal to some y plus p. Okay, so you choose two elements such that the product x y bar, x into y bar, that is xy bar, that is 0. 0 means 0 bar. Okay, in this p bar. Okay, so you choose two elements whose product is 0 bar. So what does that mean? That means, so this means that this xy plus p equal to p, right? This identity is 0 here in R naught p, and hence you can talk about okay, so yeah, so now you can talk about so see, this is the ideal, and you find out the xy plus p equal to p. So what does that mean? That means the left cosets of this cosets of this equal to this, right? P. And you know that this is final property. This is if and only if xy belongs to p, right? So this means that x comma y is an element of the prime ideal p. Okay, but as p is a prime ideal of R, we have either x belongs to p or y belongs to p, right? Prime ideals. So what does that mean? So if x belongs to, that is, so either x plus p means what? That means x plus p equal to p or y plus p equal to p, right? So that is what? So this implies either x bar equal to 0 bar or y bar equal to 0 bar in this p bar, right? And that is the thing is that we need to prove. Thus this R mount p, which is nothing but p bar, is an integral domain, right? Clear? So we started with two product of two elements is 0 inside R mod p, and we showed that at least one has to be 0. So there cannot be a zero divisor. So that means that R mod p is integral domain. Right. And conversely, you need to give the converse part also. So conversely, let R mod p is an integral domain R mod p is an integral domain. This is the converse part, and I need to prove that p is an prime ideal. Okay. So to prove something is a prime ideal, what I need to choose? So I need to check that product of 2 is right inside P, that means one of this inside C. So let x and y belongs to R, two elements, such that x into y, the product, is an element of the prime ideal P. Is the element of the ideal P. So I need to check this prime ideal. So I don't know right now is prime or not. So this, okay. So this implies what? This implies that xy plus p, this is p, right? This is the cosets are same, and that implies xy whole bar equal to 0 bar in R mod P, right? In R mod P they are 0, right? But R mod P, so what does that mean? That means x bar into y bar equal to 0 bar in R mod P, right? But R mod P is an integral domain, right? So either x bar, either one of the sorry, so one of those has to be 0 bar, right? So that is as R mod P is an integral uh, P is an integral domain, what do you have? We have either x bar, what was that? Yeah, x bar, either x bar equal to 0 bar or y bar equal to 0 bar in R mod P, right? So here x bar equal to 0 bar, what does that mean? That means x belongs to P, right? That is, this implies either x belongs to P or y belongs to P. Okay, done, right? So we choose the two elements, the product is element of the prime ideal, then we find out that at least one must be prime, right? So thus P is a prime ideal of R, right? QED. So this is very important theorem that characterize or can easily find out that what are the primary elements, what are the maximal elements. You can easily find out that. Sorry, I did not discuss what are the primary elements directly. Okay, from here. Okay. Yeah, so one example I already gave you, and of this kind of how to apply this kind of theorem. You have many more example. Some of the example you will find out in our next tutorial session. Okay. So now let us define another very important idea, and this is called maximal ideal. Maximal ideals. Okay. So maximal ideals, you remember we discussed when we were discussing these important groups, we discussed something called maximum group, maximum subgroups, right? Similar, this is a similar idea. So how to define it? So definition. An ideal M um, or rather maybe I can start so proper ideal, I should say proper ideal. So I write down should proper ideal M is said to be said to be a maximal ideal. So I am not saying the maximal ideal because it's not like unique. It's like in a ring there may be more than one maximal ideal. So that's why I'm saying a maximal ideal ideal if uh, if there is no proper ideal containing M. I mean no proper ideal of R. Okay, so R is a commutative ring. This I am already assuming. Okay, so we say that M is a proper ideal. M is a proper ideal, that also we assume that. And this proper ideal is called as maximal ideal if there is no, it is not contained inside any other proper ideals, right? So what does that mean? So that is mathematically uh, if uh, you choose some ideal I be an ideal of R such that M is a subset of I subset of R, then what happens? Then there can be two possibilities. Then either M equal to I, so the same containing M other than M, obviously. Obviously this M always contain M, right? Other than M. Okay. So either M equal to I or I equal to R. This is the possibility. Okay. So the only thing that contains M's is either M or R. But R cannot be a proper ideal, R is a full ideal, right? So the only proper ideal which contains M is the M itself. Clear? So this is the definition of a maximal ideal, right? Now again, let me give some examples before going to the many theorems. So examples. You see again that ring of integers. Now you see that we already checked that this ideal generated by primes are prime ideal, right? But you also that these are also maximal ideals for any prime number. If you take the ideal generated by prime p, pz, they are also maximal ideals for any prime. Okay. For p prime. Okay. Now how to show this is maximal ideals? So to show these prime ideals, either general prime or maximal ideals, it is enough to say that you don't have anything in between. So how do you say that? So if this ideal is sitting inside another ideal which is not a prime power, okay, so let me write down this. So maybe if this is something like that, see, okay, and see, if I equal to b, then there is nothing to prove, right? So and if p is not equal to I, so that means um, uh, it's proper, right? Then I need to show that I equal to z, then I am done. Okay. So that means so there exists some element, say x belongs to I, not inside the ideal p, right? You have an element which or rather you have an integer, say let me write down integer n belongs to I such that n not inside that ideal denoted by prime, right? So what does that mean? That means n is not a multiple of the prime number p. Is it okay? This implies p does not divide n, right? Is it okay? What does that mean? So this implies p and n are co-prime. This is one. It's okay? P does not divide n, right? So this is p is a prime number. This it has to be one. Okay. So what does that mean? That means you can use the Bézout lemma. So Bézout lemma tells you that there exist these integers k1, k2 belongs to z such that this k1p plus k2n equal to 1, right? So this is that idea we use many times. Okay. And now you see that I will show that um, um, this is element of I. Why this is an element of I? Because so this now this K1P is an element of P, obviously. Rather idle general P, whatever you wrote, what I yes, this is my capital P. Okay, and N is element of I, and hence K2P element of I, right? And also this P is inside I. So what does that mean? That means K1P plus K2N, which is element of I, right? But this is 1, so 1 belongs to I, right? Now 1 is a unity, right? 1 is a unit, and we proved that in last class. The moment unity inside the things, that means that is the full, right? It means that I equal to full ring Z here, yeah. So this is Z. Clear? Because 1 inside I means ideal, so if you multiply by any integer, that will be again inside I. So every integer inside I. Clear? So the prime ideals are also maximum ideals inside Z. Okay, I mean non-zero, yeah. And now check that, yeah. So this example 2, ideal 0 is not a prime ideal, and not a maximum ideal. It's a prime ideal, but not a maximum ideal. Maximal ideals, ideal in this is, why? Because this is sitting inside any idea, right? So properly, for example, this is inside this, right? Properly. I mean, if yeah, this is Z, obviously the full thing. So maximum, you cannot go, right? So these are examples. So so now let me discuss another fundamental theorem, whatever we discuss inside prime ideals. Here also you can characterize these things by a theorem. And what is that theorem? So theorem. So let R be a commutative ring, okay. Then an ideal M is a maximal ideal of R if and only if, what happens if and only if this quotient ring R is a field actually. For prime ideal, what we proved, that was an integral domain, right? But here we have this more property. It's a field. So what does that mean? That means that the inside the quotient ring, it has to be there. Every non-zero element has to be invertible, right? Every non-zero element has to be invertible. Then it is a field. So again, it needs a proof, proper proof, and this proof is very important because the idea is going to use many places. So now how do we prove it? Proof. So which part should I prove first? So let me assume that let M be a maximal ideal. Maximal ideal of R. Okay. And I need to prove that R more M equal to is field. So this consider this. Let me write now M bar, which is R more M. Okay. So this is I need to find out the field. Okay, so I have to choose a non-zero element. I have to find out the invertible element. I have to prove that this is an invertible element, right? So the inverse exists. So let uh, something say M belongs to M bar is a non-zero element. So what does that means? Non-zero element. That is M bar not equal to 0 bar in this R mod M, right? So that is what that means. M does not belongs to capital M, right? This is the meaning. So if M does not belongs to this capital M, then what you can do? You can obviously play the trick. What is the trick? So I will define another idea. I'll say J. This is M plus that element by small m. Okay. So this is already defined in last class. Addition of two ideals is ideal, right? So the element of the form will be from here something and from here something, right? So this is an ideal, right? So is an ideal of R, right? Now you see that your M is properly sitting inside J, right? Because you have something outside M and J is inside R, right? This is the relation we find out from M, J and R. Now uh, the maximality of M implies that um, J equal to R, right? M is maximal ideal that we already assumed. So J has to be equal to R. Now J is equal to R means what? So J equal to yeah. So maybe I need one more thing. So let me. Okay. Yeah. So I need this unity. I think. Yeah. So um, otherwise the maximum ideal may not exist, right? It may not sitting inside the maximum ideal. Yeah. So this thing I need to assume here. Okay. Commutative unitary ring. Yeah, I need that. Okay. And maybe I will give you proof that this is needed indeed. Okay. Okay. So the maximality of these, so that means is 1 is an element of R, right? Which is element J also. So what does that mean? That means you can write 1 in terms of something from here, something from here, right? So 1 can be written as some m into k plus yeah, so plus something x where x belongs to m, capital M. Okay, this is okay. So what does that mean? So when you go modulo 1 bar, so that is the 1 bar is nothing but m into k yeah. So, okay, so I should say this is m bar actually. So m is the pre-image. So m bar is nothing but m plus capital M. Okay. Yes. So now yeah. So this is m bar k bar which is inside R mod M. So inside R mod M, what happens when you go modulo M, this vanishes because X is element of M. So the only thing remaining is 1 bar equal to M bar K bar, right? But 1 bar is the identity inside R mod M, unity rather. So what means that? Means that M bar is invertible in R mod M. Okay, and we choose M bar is a arbitrary element, right? This is arbitrary element. So thus every non-zero element of R mod M is invertible. So R mod M is a field. Clear? Yeah. So now conversely, you need to give converse proof also. So conversely, what happens? So let R mod M be a field. I need to prove that M is a maximum ideal. Okay. So and there exists an ideal set J in J subset of this R such that we have M is a proper subset of J subset of R. Okay, this is the assumption I am assuming. Now to prove M is a maximum ideal, I need to prove that J equal to R. This is the thing I need to prove. Okay. Now you see that J is ideal containing M, right? So inside R mod M, you remember R mod M is a quotient ring, right? First, but what are the ideals of R mod M look like? The fourth assumption theorem, which we proved last time, that tells you that the ideals of these are of the form J mod, right? Right? These are the ideals of this. Okay. And now the assumption tells that this is a field, right? And we also feel that inside a field, what are the only ideals? The only ideals are zero ideals or the full ideal, right? So as R mod M is a field, this J mod M is either zero ideal, zero bar, or full R mod M, right? But J mod M cannot be zero bar, right? As J not equal to M, right? Because I assume that J properly contain M's, right? So what does that mean? That means that J mod M equal to R mod M. And this implies J equal to R. Okay, and thus M is a maximal ideal. Of R. Clear? So this is a very nice way of concluding something is a maximum ideal or not. You go more below the ideal and check that is a field or not, and then you are done. So for example, what I prove for integers, we can have this direct proof. So we prove that any prime ideals generated by p prime number, it was a prime, also is a maximum ideal. Why? Because whenever you go modulo this, so that is z mod pz, and you see that is a field, right? You already know this thing, prove it. So what does that mean? So this is integral domain and finite integral domains are field, right? hence this is a maximum ideals. Okay. Now example 2, we find out that this the ideal generated by x, right, in Zx is a prime ideal, right? That we give example because Z mod Zx mod x is and z, right, and this is integral domain. But you see that this is the integral domain. This is not a field, as z is not a field, so this is if and only, right, not a maximal ideal. Okay, clear? So these are the examples. You can have lots of other examples, obviously. Yes, so one more important idea that I need to discuss, that whenever you have a commutative unitary ring, then any whatever proper ideal you choose, that contains inside a maximal ideal. That is the important idea, and the proof is actually using the Jones lemma. Whatever you want to find out the maximal element, you need to use the Jones lemma. Okay, so maybe I should say that thing, and then I will stop today's class. So theorem. So let um, let R be a unitary ring. Okay, and then every proper ideal of R is contained, means it inside in a maximal ideal. Okay, and proof is essentially Jones lemma. We will have to use Jones lemma. So I need to find out the poset, right, proper set, so that I can use the Jones lemma. So let me find out. It's like this is a collection of say, what I say, all proper ideals of R containing so let start with the ideal. So let I be a proper ideal of R, and I need to find out that I is the inside some maximal ideal, right? So what I am doing, I am finding a poset where I can use the Jones lemma. So so let me write down the collection all proper ideals of R containing I. This is my set. This is non-empty, right? So as I belongs to this, so this collection is non-empty. Okay, so you have a non-empty collection, and also is naturally also this is a poset, mean partial error set, uh, that the ordered by inclusion, that set inclusion. Okay, so you have set inclusion that will give you the poset structure, right? And now you remember to use Jones lemma, what I need to find out? We need to find out that every totally ordered subset, or whatever we call chain, if the every chain has a maximal element, then the whole thing is a maximal, right? So so let C be a chain in P. Okay, so this is my symbol. So I'm assuming a chain in P, and I need to find out chain means. So inside C, this is totally order. So if you choose any two ideals, either first one is sitting inside second one, or second one is sitting inside first one, right? So then you find out, you define an ideal, say something, say m dash. Okay, mine in maximal, right? So m dash is the union of these ideals, whatever, so maybe a is ideal such that a is an element of C. Okay, so you call it all the ideals of C and take the union. Okay, so this m dash, now this homework you can easily check the m dash is a ideal, an ideal, because this is union of ideals where each of those things inside, they are in the total order set, right, inside C. So union has to be an ideal. So it's an ideal of this R. This ideal of R, and ideal of R, and also not only that, m dash is also um, sitting inside this. Okay, so where is the m dash that I need to find out? Okay, so um, yeah, so I need to first check that. See, this is ideal, this is not a problem, but one thing I need to check properly whether this is proper ideal or not. If it's not a proper ideal, then this is not an element of P, right? So and m dash is element of P that I need to find out, right? So this part I need to give a proof. Ideal, I hope you don't need a proof, you can easily prove it. To prove something is ideal, what you need to check? You need to check that this is a subring, like if you choose two element, then minus thing is the element of this. Okay, and then product. And the important thing is that this is closed, right? So closure property means what? Whenever you choose anything outside m dash, that will absorb it, right? But this is obvious. The main thing which is left is that it is an element of this. What does that mean? What is P bar? So this is C, proper ideals, right? So I dash, obviously I always inside m dash, because m dash is union of those things, and I is also one of the element, right? So yeah. Oh no, sorry. This is, I will say later. Okay, not now. Yeah, now I don't know. Yeah, that I will come later. That I will come later. Okay. Okay. So now Jones lemma. I need to find out using Jones lemma. So I need to check that this is an element of P. Now, how do you check that this is not a proper ideal? So claim. So what is my claim? So my claim is that m dash is a proper ideal, right? That is m dash not equal to R. This is my claim. So I will prove by contradiction. So if not, that is m dash equal to m. Suppose m dash equal to m, the full thing. Then what happen? Then I assume that one, right? Remember, one is inside uh, unitary ring. So that is important, I think. Then this one is element of m dash. This is I required, right? So one is element of m dash, and what is m dash? M dash is union of this A belongs to C, right? So if one is union of some ideals, so what does that mean? That means one belongs to A for some A, which is element of C, and C is a subset of P, right? But this is a contradiction, right? Because inside P you have all those ideals which are proper ideals. So this is a contradiction. This is a contradiction. Dixon as P contains proper ideals. Proper. Okay, so this is a contradiction. So what does that mean? That means that that one cannot belongs to that M dash. So this means what? So thus M dash cannot be equal to R. So M dash is a proper ideal, right? Okay. So that is the important thing I need require, right? So thus this the chain C has an upper bound, or rather maximum whatever upper bound in P, right? So by Jones lemma, what does Jones lemma said? Um, Jones lemma. This P has an upper bound. The upper bound of C, if every chain has a maximum element, upper bound, then the full poset has a maximum element, right? So as an upper bound, or you can say also that maximum element, say M. This M may be different from M dash also, right? But this maximum element upper bound, right? So what does that mean? That means M belongs to this. So I is something sitting inside M, right? Because inside P you have all the ideals which are proper ideals and which contains I. So I is inside M, right? And M is the maximum element. So what does that mean? That means whenever you have a unitary ring, you must have every I proper ideal must be sitting inside some maximum ideals, and that is very important idea. Okay, so I will stop this thing. Just telling one last uh, remark or whatever note. You say that if you commentative ring, the maximum ideals are always primary, right? So um, every maximal ideal in a commutative ring is a prime ideal. It's obvious. Why is obvious? Because something is a maximum ideal means the quotient ring is a field, but every field is an integral domain, and hence the quotient ring is integral domain, and hence the ideal is a prime ideal. But the converse is not true. That I already proved it. Okay. Um, every maximum ideals it's prime ideal, but every prime ideal is not a maximum ideal. Okay. And the converse is not true in general. In general, not true. There are some conditions which will implies is true. Okay, so by this I will stop today's class. Bye.